Right now, a proton inside the Large Hadron Collider is circling beneath the Swiss countryside at 99.999999% of the speed of light. Its clock has nearly stopped. Its mass has ballooned to 7,000 times what it was at rest, and it still has not reached light speed. It never will. We are about to walk through what would actually happen to your body, your eyes, and your sense of time if you tried to chase that limit. From the first gentle push of acceleration through the moment the universe itself turns into a weapon aimed directly at your face. If this kind of journey grabs you, like and subscribe. The ride begins now. The question sounds simple. What would really happen if you traveled at the speed of light? Every science documentary eventually bumps against it. Every physics teacher fields it at least once. The answer they usually give is nothing can travel faster than light, and then they move on, as if that settles anything. It does not settle anything. It sidesteps the actual question entirely, which is, what happens during the attempt? What would you see? What would you feel? What would be happening to your body, your clock, your universe, as you closed in on that limit? Movies have their answer. The stars stretch into white streaks. A tunnel of light forms ahead of you, and you vanish into it with a satisfying whoosh. That image has been reprinted so many times that most people accept it as a rough approximation of reality. It is not. The actual physics of high-speed travel is stranger, more beautiful, more violent, and in several places more disturbing than anything any film has put on screen. The movies borrowed the aesthetics of speed and forgot the science. This journey is going to fix that. We are going to accelerate, slowly at first, then harder, then toward the edge of what physics permits, pausing at each milestone to take stock of what the universe looks like from inside a ship, moving at a significant fraction of light speed. Some of what you will find is awe-inspiring. Some of it is lethal. Some of it will quietly dismantle assumptions you have held since childhood about how time works, how space works, and what it means to be somewhere at a particular moment. The journey begins gently. At low fractions of light speed, the ride is smooth, and the sky looks almost normal. The physics is already running in the background, reshaping things at levels too subtle for human senses to detect. Push further, and those subtle shifts become impossible to ignore. Colors slide across the spectrum. Stars start to move in directions they have no business moving. Time, that reliable companion, starts to fall behind. And then there is the question of the universe itself fighting back. Space is not empty. The void between stars contains material, diffuse, and thin, but at high enough speeds that material transforms into something that will kill you in seconds if you let it touch you. Even the smallest specks of dust, the kind that drift harmlessly through interstellar space for billions of years, become grenades at the right velocity. There is also the question of your own body. Human physiology was built for one gravitational field, one atmospheric pressure, one quiet, ordinary surface to stand on. The demands of accelerating to a significant fraction of light speed place forces on the body that have very specific and very absolute limits. Those limits matter for everything that follows. What this journey requires is honesty. Honest physics, walked through step by step, at every speed, milestone from 10% of the way to light, all the way up to the fractions that approach the limit itself. Each step will reveal something the comfortable version of this story leaves out. The speed of light is approximately 186,000 miles per second. That number is about to become very personal. In the summer of 1905, a 26-year-old patent clerk in Bern, Switzerland, submitted a paper to a physics journal that changed everything. Albert Einstein had no laboratory, no experimental apparatus. He worked on the problem during his lunch breaks and in the evenings, using nothing more than mathematics and a willingness to follow logic wherever it led, even when it led somewhere unsettling. The paper was called On the Electrodynamics of Moving Bodies. It began with two premises so simple they sound almost obvious, and then systematically demonstrated that together They require the universe to work in a way that violates every human intuition about motion, time, and space. The first premise: the laws of physics are the same no matter how fast you are moving, as long as you are not accelerating. A candle burns the same way on a stationary table as it would on a perfectly smooth ship gliding across still water. Physics does not care about your speed. The second premise: the speed of light in a vacuum is always the same for every observer, regardless of how fast they are moving. Always approximately 186,000 miles per second. If a spaceship fires a laser beam forward while traveling at 90% of light speed, the laser does not travel at 190% of light speed. It travels at exactly 100%. The person on the ship and the person watching from a stationary position both measure the exact same speed for that beam. These two premises together create a logical trap with only one exit. If the speed of light is constant for everyone, and you are moving toward a light source, you cannot be adding your speed to the light's speed. Something else must be compensating. That something is time and space themselves, bending to keep the numbers consistent. Time slows. Distances contract. The universe distorts its own geometry to protect that speed limit. Einstein was not describing something that happens to light. He was describing something fundamental about the structure of reality. The speed of light is not merely how fast photons travel, it is the speed of causality itself, the maximum rate at which any cause can produce any effect, anywhere in the universe, for any reason. It is the speed at which the present propagates into the future. This is why exceeding it is physically impossible in the deepest sense. Exceeding it would mean outrunning causality, arriving somewhere before the cause that sent you, which unravels the logical structure of existence entirely. The mathematical tool that quantifies all of this is called the Lorentz factor. Its symbol is gamma, and the formula produces a number that stays close to 1 at low speeds, climbs slowly through the middle range, and then rockets toward infinity as velocity approaches the speed of light. At 10% of light speed, gamma is essentially 1. At 50%, it is 1.15. At 90%, it reaches 2.29. At 99%, it is 7.09. Each of those numbers carries a weight that will become clearer as this journey progresses. That single factor governs how much your time slows, how much space contracts, how much energy you need to keep accelerating. It is a single dial controlling the entire physics of your trip. Right now, it reads close to 1. That is about to change. Assume the ship accelerates at 1 gravity. That is the same pull you feel standing on the floor right now. Comfortable, sustainable. The kind of acceleration the human body can handle indefinitely. At that rate, it takes about 35 days to reach 10% of light speed. 35 days of gentle, steady push, and you are covering roughly 67 million miles per hour. At that speed, Mars, which typically takes 6 to 9 months to reach with conventional rockets, is now hours away. You would pass the orbit of Mars before lunch. The asteroid belt, that wide band of rocks and debris between Mars and Jupiter, flashes by in a matter of hours as well. The outer planets, which take spacecraft years to reach currently, would fall behind in days. The outer edge of our solar system's most distant reaches, where the frozen bodies of the Oort cloud drift in the dark, is still roughly a year and a half away, even at this speed. The solar system is still enormous by human standards, but the scale of what 10% of light speed does to travel times is already striking. The Lorentz factor at this speed is 1.005. That decimal is almost invisible. Technically, time on your ship is running very slightly slower than time on Earth. If you spent an entire year traveling at this speed, you would age about 364 days and 7 hours, while 12 months passed at home. The difference is not measurable by a wristwatch. It would not change any plans you had made. The universe at this speed is gracious, offering up extraordinary velocity while asking almost nothing in return. The view from the window still looks essentially normal. Stars ahead are unchanged to the naked eye. Stars behind look the same. There is no dramatic blurring, no colored halos, no visual strangeness. The physics of what is happening remains invisible, tucked beneath the threshold of perception, waiting for more speed to make it show itself. That waiting period is shorter than you might think. The changes begin gradually, but they begin. The relativistic Doppler effect, the same principle that makes a car horn shift pitch as it passes you at speed, applies to light as well. At this moment, the shift is too small for human eyes to register. Stars ahead are technically a fraction bluer, stars behind a fraction redder, but fraction is the operative word. Nothing in the sky declares itself different. Inside the ship, the feeling is simply motion, steady, manageable, unremarkable. The hum of whatever propulsion system carries you, the weight of one gravity, keeping your feet on the floor, the normalcy of the air around you, all of it ordinary, all of it calm. At 10% of light speed, you are already in a regime that no human being has ever approached. The fastest any crewed spacecraft has ever moved is roughly 25,000 miles per hour. You are going approximately 2,600 times faster than that. And the physics has barely noticed you yet. Push the speed higher, though. Add another 10 or 20% of the speed of light, and the universe starts to respond. The colors are the first thing to go. You have crossed 30% of the speed of light. The Lorentz factor is 1.05 now. Still modest, still quiet. But something has changed in the sky, and once you notice it, you cannot unsee it. The stars ahead are different colors. The change is real and visible. Stars that were white or pale yellow now carry a blue tint, some pushing toward violet. The color temperature of the light reaching you from the forward direction has shifted toward higher frequencies. A glance behind reveals the opposite. Stars that were white now carry warm orange and red tones, their light stretched toward the lower end of the spectrum. The sky has split into two color palettes, divided by the direction of your travel. What you are witnessing is the relativistic Doppler effect. Every amateur astronomer knows the basics of the Doppler effect from sound. The pitch of a siren rises as the source approaches and falls as it recedes. Light behaves the same way. When you move toward a light source, the waves compress, squeezing toward the high-frequency, short wavelength blue end of the visible spectrum. Move away, and the waves stretch, pulling toward the low-frequency, long wavelength red end. At everyday speeds, this effect is too small to see in starlight. At 20 to 30% of light speed, it becomes unmistakably visible. The blue shift ahead is gentle at this speed. Stars do not vanish into ultraviolet. Their visible colors simply slide a step toward blue on the spectrum. White stars pick up a hint of blue-white. Yellow stars drift toward white. The shift is subtle, but it is real, and it carries information that goes beyond aesthetics. Those colors are telling you something about time. Light is not instantaneous. Every photon you see left its source at some point in the past, and it has been traveling toward you ever since. When you move toward a star, you are effectively shortening the distance those photons must travel to reach you, compressing the time between successive wave crests, increasing the frequency you detect. When you move away, the reverse happens. The color of a star, in other words, encodes information about your relative motion through space-time. The universe is marking your speed directly on your sky. The red-shifted stars behind carry their own message. As your speed increases further, the red shift behind will deepen. Stars that are yellow will turn orange. Orange will turn red. Red will fade toward the infrared, invisible to human eyes. The light still arriving, but at frequencies the eye cannot detect. At some point, stars behind will simply vanish from view, not because they are gone, but because their light has shifted beyond the visible range. None of this is metaphor, none of it an optical illusion. The light genuinely carries different frequencies depending on your direction of motion. Your speed is physically encoded in the wavelengths hitting your eyes. At 30% of light speed, the sky is still mostly recognizable. The constellation shapes are intact. The stars are just wearing different colors. The geometry of the universe around you has not yet made its dramatic moves. Speed is still building, and the geometry is about to get strange. This one is harder to expect. The colors shifting felt intuitive once explained, a simple consequence of wave compression and expansion. What happens next to the sky has no everyday analogy. Nothing in ordinary life prepares you for it. The stars are moving, or rather, they appear to be moving, pulling toward the front of the sky as if drawn there by some invisible force. Stars that were once distributed broadly across your field of view, spread around the sides and behind, are now crowding forward. The rear sky is thinning. Constellations you saw perfectly clearly behind you are starting to drift toward the horizon, then forward. The sky is rearranging itself, and the only thing causing it is your velocity. This effect is called aberration of starlight. It has been observed since the 18th century, when astronomers noticed that the apparent positions of stars shift slightly as Earth moves through its orbit around our star. At orbital speeds, the effect is tiny but measurable. At relativistic speeds, it becomes visually overwhelming. Here is what is actually happening. Photons travel at light speed in every direction through space. When you are stationary, they arrive at your eyes evenly distributed across the sky. When you start moving, photons from the side are hitting you slightly from ahead because you are running into them. The faster you go, the more dramatic this angular shift becomes. A photon that would arrive exactly perpendicular to your path if you were standing still now appears to arrive from a shallow forward angle. The effect compounds with speed. More and more photons appear to come from ahead, and the angular distribution of light across your sky concentrates forward. At 50% of light speed, roughly half the sky visible behind you has already shifted. Stars that were at 90 degrees to your path, arriving perfectly from the side, now appear to come from ahead of perpendicular. The rear sky loses density. The forward sky gains it. The geometry creates a crowding effect that has nothing to do with the stars actually being there. Stars are not moving. The universe is not rearranging itself. Photons from all directions are hitting your eyes from new angles because you are running through them at half the speed of light. The entire celestial map has folded forward around your direction of travel. The brightness of the forward sky also increases. More photons arriving from ahead means more light entering your eyes from that direction. The forward sky becomes noticeably brighter. The rear sky dims. If you turn to look behind you now, you are looking into a sky that has been robbed of much of its light, starved by the geometry of your motion. There is something philosophically striking about this. The stars have not changed. The physics of photon propagation has not changed. The only thing that changed is your velocity, and yet the entire sky looks different because of it. The universe you perceive is not a fixed, objective picture that every observer sees identically. It depends on how fast you are moving. Reality, at least the visual version of it, is personal. This is only the beginning of how personal it is going to get. 50% of light speed brings its first serious revelation. Your clock is starting to disagree with every clock you left behind. Half the speed of light, the Lorentz factor, is 1.15. That decimal does not sound dramatic, but follow it forward and see where it goes. For every year that passes on your ship, 1.15 years pass on Earth. Run that ratio for 10 years of travel, and you return to find that 14 months have passed that you did not live through. 10 years of your life maps to 11.5 years of everyone else's. The gap is small, but it is real, it is growing, and it will never close. This is time dilation. The effect was built into Einstein's equations from the start, but here at 50% of light speed, it has crossed the threshold from mathematical abstraction into something you could feel if you knew to look for it. Your heartbeat is exactly normal. Your clocks tick at their usual rate. Nothing inside the ship gives any indication that time is moving differently for you than for anyone else. From your perspective, everything is fine. From Earth's perspective, You are aging at a rate of about 11 months for every 12 that pass there. Try to call home. Any signal you send travels at light speed, but you are moving away from Earth at half that speed. The message takes longer to arrive than it would if you were stationary. When it does arrive, it is red-shifted, the carrier wave stretched by your recession, and if they call you, the signal catches up to your ship slowly. The conversations grow stretched and strange, separated by signal delay and by the growing temporal gap between your two world lines. The emotional weight of this has no equivalent in ordinary human experience. Every increase in speed you make from this point forward deepens the gap. Every fraction of light speed you add to your velocity is a fraction of shared time you are surrendering. Accelerate to 70% and the ratio worsens. Push past 90 and the gap widens into years per journey year. The people you left behind are living their lives at full speed, while yours runs slower by a factor that grows with every increase in velocity. There is no reversing it. When the ship eventually decelerates and you return, the time difference is permanent. You will not have aged back. The gap is banked into space-time geometry, as real as any physical distance. The twin who traveled genuinely arrives younger. The clocks genuinely disagree. Every second of the discrepancy is locked in and irrecoverable. For now, at 50% of light speed, the gap is manageable. A 10-year journey produces a 14-month difference. You can plan around it, factor it into goodbyes and reunions and expectations. The mathematics is cooperative, the stretching gentle enough that the mind can hold it without too much strain. But 50% of light speed is not the destination. You are still accelerating, and the relationship between your clock and everyone else's is not the only thing that is starting to break down. Space itself is about to become the enemy. The void between the stars, so peaceful looking out that forward window crowded with blue shifted light, is full of something that at low speeds is essentially harmless. At the speeds coming next, it is not. The phrase empty space is wrong in a way that becomes dangerous at high velocities. Space is not empty. Even in the relatively clear region around our solar system, the interstellar medium fills every cubic centimeter with material, mostly hydrogen, roughly a fifth of an atom per cubic centimeter on average, which sounds like almost nothing. The thin atmosphere atop a mountain has around 10 billion molecules per cubic centimeter by comparison. The interstellar medium is genuinely sparse. Sparse is not zero, and at high fractions of light speed, the mathematics turns sparse into lethal with remarkable efficiency. At 30% of light speed, your ship is slamming into hydrogen atoms at energies comparable to the particles inside a major particle accelerator. Each atom carries relativistic kinetic energy, measured in hundreds of millions of electron volts. Individually, they are submicroscopic and deliver vanishingly small energy transfers, but they are arriving in quantities that cannot be ignored. Research published in the journal Acta Astronautica calculated the radiation exposure for a crew traveling at 70% of light speed through average interstellar medium. The unshielded dose exceeds 100,000 rem per second. The entire concept of exposure limits becomes irrelevant at that figure. The fastest recorded radiation deaths in nuclear accidents occurred at doses of around 50,000 rem to the whole body. This is double that delivered every single second. To understand what that means in practice, a person standing inside the chamber of a running nuclear reactor with no shielding would receive roughly 100 to 500 rem per hour, depending on the reactor. At 70% of light speed through open space, the hydrogen alone delivers a fatal dose in the time it takes to blink. The radiation arrives in a specific way that makes it especially damaging. The hydrogen nuclei, individual protons, hit the hull and produce secondary particles, neutrons, pions, muons, gamma rays. A thin metal hull is worse than nothing for some of these, because it produces a spray of secondary radiation that irradiates the interior more thoroughly than the primary beam would have alone. The ship becomes a particle accelerator aimed at its own crew, and hydrogen is only part of the problem. The interstellar medium also contains helium, trace heavier elements, electrons, and fields of ionized plasma from stellar winds. Each component behaves differently at relativistic speeds. Helium nuclei, being heavier, deposit more energy per impact. The ionized plasma creates electromagnetic drag, an additional source of heating on the hull. Shielding is theoretically possible. Dense material at the bow of the ship, heavy enough to absorb and scatter the incoming radiation before it reaches occupied compartments. Water is surprisingly effective for this purpose, hydrogen rich enough to scatter nuclei, and useful as a life support consumable besides. But the thickness required scales badly with velocity. At 30% of light speed, a few centimeters of titanium provides meaningful protection. At 80%, you need meters. At 90%, you need tens of meters of dense shielding at the leading face of the ship. The shield itself becomes one of the primary engineering challenges of the entire vehicle. None of this shows up on the window. The view remains beautiful. Stars bunched forward, colored blue, bright and vivid against the dark. The danger is invisible, arriving as particles you cannot see. And the danger is about to get more concrete. Hydrogen atoms are the universal threat. They are everywhere, unavoidable, and at speed, they transform into radiation. But there is a second category of hazard in the interstellar medium that is in some ways more viscerally alarming, because it is larger, more individual, and its effects are more sudden. Dust. The space between stars is not sterile. It is threaded with clouds of solid particles, grains of silicate, graphite, frozen water, and complex organic compounds. These grains are small, typically 10 trillionths of a gram, objects so tiny that a single grain is invisible without a microscope. In the interstellar medium of our galaxy, they arrive at roughly 100 particles per square meter per second, and that estimate assumes you are moving at half the speed of light. At that speed, each grain strikes the hull with kinetic energy far exceeding anything in its rest mass. The grain is depositing its entire kinetic energy at the end of its penetration depth inside the material, exactly as a bullet deposits energy by decelerating through tissue. The energy is enormous relative to the size of the impacting particle. The result is a micro-explosion, a tiny burst of vaporized hull material, a spray of secondary particles, a shock wave propagating through the metal. Individually, each impact is small, but at 100 impacts per square meter per second across an entire hull, the forward face of the ship is being continuously ablated. Molecules of hull material are boiling off. The leading edge is eroding at a rate that accelerates with speed. Over the course of a multi-year interstellar journey, a ship traveling at half the speed of light with no shielding would lose significant material from its forward surfaces. There are also larger particles. Interstellar space contains grains that mass at millionths of a gram or more. Still tiny on human scales, but at half the speed of light, a millionth of a gram arriving at your hull carries kinetic energy in the range of tens of kilojoules. That is roughly the energy of a grenade. A grain 1,000th the size of a grain of sand, invisible under most optical microscopes, detonates against your hull with the force of an explosive. The engineering implications are severe. The forward shielding must handle both radiation and physical impacts. A solid ice shield has been proposed for both purposes. Hydrogen rich enough to scatter the incoming nuclei, and self-healing in a limited sense, since a dust impact vaporizes some of the ice, but the remaining material fills the void. Other proposals involve sacrificial layers of aerogel, carbon fiber composites, or electromagnetic dust deflectors using magnetic fields to push charged particles off course. Though neutral grains cannot be deflected electromagnetically, every additional fraction of light speed increases the impact energy of each grain proportionally to gamma squared. The dust that was merely erosive at 50% becomes structurally threatening at 80%. The ship's leading face is locked in a continuous war with the medium it is traveling through. The interstellar medium wants to stop you. The radiation wants to kill you. And threading through all of it is the quieter question of whether the biological machine doing the traveling can survive the demands of getting to these speeds at all. The human body has limits. They are absolute, and they are coming. The most extreme speed in the universe means nothing if the thing doing the traveling falls apart before it gets there. Every engineering challenge of interstellar travel has a solution that can at least be imagined. Shielding thicker, materials stronger, reactors more powerful. The human body presents a different kind of problem. Its limits are not set by current technology. They are set by biology, and biology is not negotiable. Acceleration is the core issue. To reach a significant fraction of light speed, a ship must push its occupants continuously for a very long time, or briefly at much higher forces. Both approaches have costs that fall directly on the body. One gravity of continuous acceleration is comfortable. It is the force you are under right now, sitting or standing on the surface of this planet, unremarkable and sustainable. A ship maintaining 1g acceleration provides a reassuring feeling of weight, allows normal movement, and prevents the physiological deterioration that comes from prolonged weightlessness in space. At 1g, it takes approximately 1 year of continuous acceleration to reach roughly 77% of the speed of light. That is a generous timeline, spread across months of tolerable conditions, but a trip to a nearby star and back would require years of maintained thrust. Push the acceleration higher, and the timeline compresses. 2 gravities cuts the time roughly in half. 4 gravities roughly in half again. Athletes and fighter pilots train to handle brief periods of elevated forces. Modern fighter aircraft can pull 8 to 9 gravities for seconds at a time. Trained pilots in pressure suits endure this with gritted teeth and specialized breathing techniques designed to prevent blood from draining from the brain. Untrained individuals typically lose consciousness at around 4 to 5 gravities. At 10 gravities of sustained acceleration, consciousness lasts seconds. The blood pools so rapidly toward the lower body that the brain is deprived of circulation, and the lights go out within moments of the force being applied. At 50 gravities, blood vessels begin to rupture from the hydrostatic pressure differential. Organs shift against their connective tissue. The spine compresses under loads it was never designed to bear. At 100 gravities, the outcome is rapid and irreversible. Bones shatter. The architecture of the internal body, every organ held in place by tissues calibrated for 1 gravity, is crushed by its own weight. Nothing inside survives intact. This creates a hard boundary on the problem. To reach the highest fractions of light speed on timescales shorter than a human lifetime, acceleration must be extreme. But extreme acceleration kills the human occupant. The answer, if there is one, involves either biological solutions that have never been achieved, such as suspended animation or liquid immersion to distribute force evenly, or accepting the gentle timeline of 1g and preparing for a multi-year journey with all the radiation, dust, and temporal isolation that entails. The mathematics of 1g travel at least offers something consoling. The traveler does get there. Years pass, the Lorentz factor climbs, time dilation grows. The journey is long but survivable, provided the shielding holds, provided the dust does not scour the hull bare, provided the radiation does not penetrate the forward armor. 90% of light speed lies ahead, and at 90%, the universe does something that nobody could have predicted without the mathematics of relativity. 90% of light speed. The Lorentz factor has climbed to 2.29. Every second of your time now corresponds to 2.29 seconds outside, but the time dilation, significant as it is, has been temporarily upstaged by what is happening visually. The sky at 90% of light speed looks like nothing in any scientific textbook's diagram. It looks like something out of a fever dream. In 1959, a physicist named James Terrell worked out something surprising about how fast-moving objects appear to an observer. Before his paper, the assumption was straightforward. An object moving at high speed would appear compressed along its direction of travel, squashed, because of the Lorentz contraction. Terrell showed this was wrong. or rather incomplete. The combination of light travel time from different parts of the object and relativistic effects creates the appearance of rotation rather than compression. An object moving past you at 90% of light speed does not look squashed. It looks rotated, as if you are seeing its far side, as if the geometry of space has tilted it toward you. The same principle applies to the stars around you. The entire sky, already compressed forward by aberration, now shows a rotational distortion. Star patterns ahead look twisted, the familiar constellations warped into unfamiliar shapes beyond the simple forward crowding. Objects seem to angle themselves toward you. The fabric of the visual sky has lost its ordinary geometry. At the same time, the forward stars have shifted far enough toward blue that some have passed entirely out of the visible spectrum and entered the ultraviolet. They are still there, radiating furiously, but your eyes cannot detect them. The forward sky has actually begun to thin in the visible band from the top end, even as aberration continues to crowd stars inward from the sides. Then something else enters the picture. Normally invisible to human senses and barely detectable by all but the most sensitive radio telescopes, the cosmic microwave background permeates the entire universe at a temperature of 2.7 Kelvin. It is the afterglow of the Big Bang, stretched by billions of years of cosmic expansion into microwaves. At rest, it is as invisible as you can get. At 90% of light speed, the forward cosmic microwave background has blue shifted far enough that its peak frequency has climbed from the microwave range into the infrared. It has crept almost to the edge of human vision, not quite visible yet, but close. The result is an eerie glow suffusing the forward sky, a wash of near-infrared radiation that cameras can capture if not eyes. The universe's oldest light, the first photons ever to travel freely through space after the Big Bang settled, is now arriving at your ship, transformed by your velocity into something approaching the visible range. The dust impacts are intensifying. Each grain carries more than 5 times the kinetic energy it would at low speed, meaning every impact is more than 5 times as energetic as it would be at moderate velocity. The hull armor is working hard. The radiation dose from the interstellar medium at this speed, without shielding, would kill an unprotected person within seconds. All of this happens simultaneously, a cascade of effects reinforcing each other as the speed climbs. And then the colors do something no human eye has ever seen outside a computer simulation. Scientists who study high-speed travel face a fundamental problem. They cannot run experiments at 90% of light speed using anything larger than a subatomic particle. They cannot send a camera on a near-light-speed spacecraft and photograph what the sky would look like. Instead, they simulate it. Research groups, including a physics team at a university in Canberra, Australia, and a researcher named Daniel Weisskopf working on relativistic rendering, built computational models to answer a precise question. If a human observer with human vision accelerated to extreme fractions of light speed, what would the sky look like, spectrally and spatially, at each stage? The results produced what researchers call the rainbow effect, a sweep of color transformation that rolls across the visual field as velocity increases. Begin at rest. Stars have their natural colors, blue supergiants burning at tens of thousands of degrees, yellow stars like our own sitting at moderate temperatures, red dwarfs at the cool end, orange subgiants scattered between. The sky is a diverse palette, if you know where to look, mostly washed out by distance into white and pale points. But the underlying temperature information is there in the wavelengths. Start accelerating. The forward stars begin to blue shift. A yellow star ahead picks up a blue-white tint. A white star starts to look distinctly blue. As speed increases, the shift deepens. By 50% of light speed, the stars ahead have slid noticeably through the spectrum. By 80%, stars that started in the blue range have shifted completely out of the visible band, their light now arriving as ultraviolet that the human eye cannot process at all. Those stars vanish from the visible sky entirely, replaced by nothing, as if space ahead has darkened in patches. At the same time, stars, at the very edge of visibility in the red, have shifted into the blue and green, and now become visible as new blue points where there was nothing before. Stars that emitted heavily in the infrared, invisible at rest, have had their emission pushed into visible wavelengths by the blue shift. The forward sky is simultaneously losing stars it had and gaining stars it could not see before. Behind the ship, the mirror image unfolds. Orange and yellow stars fade to red. Red stars bleed into the infrared. One by one, the stars behind drain of visible color, their light shifted past the red end of the spectrum into wavelengths the eye cannot detect. The rear sky empties of color before it dims, turning a deep and fading red before going dark altogether. What the simulations show is that this process does not happen uniformly. Sharp spectral emission and absorption lines in the stars, features characteristic of specific elements in stellar atmospheres, slide through the visible band at different rates depending on the star's original spectrum. The result is not a smooth gradient but a kind of smearing, a painted-on sweep of hues that pulls through green and into blue-violet ahead while bleeding from warm orange into invisible red behind. Stars blink out in the visible range only to reappear shifted. Stars emerge from darkness where there was nothing before. The universe becomes an abstract composition, no longer the familiar arrangement of point source white lights your ancestors mapped into constellations. It is a chromatic event, alive with motion you caused simply by moving through it. And the rainbow effect is only the beginning of what higher speeds do to human perception of the cosmos. The number 7 sits quietly in an equation, a single symbol among several, no more alarming on the page than any other coefficient. But at 99% of the speed of light, that number is the gap between the world you knew and the world waiting for you when you slow down. The Lorentz factor at this speed is 7.09. Every year that passes on your ship corresponds to 7 years on Earth. The clock on the wall ticks normally. Your heartbeat feels normal. Breakfast takes the usual amount of time, and the universe outside your window has compressed into a blazing forward cone of blue shifted light. Nothing inside the ship announces the scale of what is happening. But while you eat one meal, 7 meals pass for the people back home. While you sleep one night, 7 nights pass for your children. Consider what the journey to the nearest star system actually means at this speed. The distance to Proxima Centauri is about 4.24 light-years. At 99% of light speed, you cover that distance in slightly more than 4 years from Earth's reference frame. Your personal time, contracted by the Lorentz factor, compresses that journey into roughly 7 months. You depart. You travel for what feels like most of a single year. You arrive. While you were in transit, more than 4 years passed on Earth. 4 years is a childhood. It is most of a high school career. It is enough time for a relationship to transform completely, for a parent to age meaningfully, for a city to look noticeably different from the one you left. And that is only the outbound leg. Turn around. Make the return trip. Your total journey time feels like 14 months, maybe slightly more with any time spent at the destination. The calendar back home has advanced by 9 years. A child who was 8 when you left is now 17. A colleague who was in the middle of a career is approaching retirement. A friend who was healthy might not be. None of this is loss through neglect or distance in the ordinary sense. It is not that you were absent and time passed, the way someone is away at sea or working in a remote location. The mechanism here is fundamental geometry. Your world line through space-time moved at a different angle than theirs. The geometry of space-time, not any human failing or failure of technology, created a gap in shared experience that cannot be undone by any journey back. The physics does not offer a version of this that is easier emotionally. There is no adjustment to the ship's parameters that softens the temporal separation. Every additional fraction of speed you add past 99% deepens the ratio. Every mission that uses the time dilation to make long-distance travel manageable for the crew is, by the same mathematics, making it devastating for everyone else. At 99% of the speed of light, you can reach nearby stars on a human timescale. You will arrive young and capable and ready. The people waiting for your return will be older by 7 years for every year of your journey. That trade is not hypothetical. It is not a thought experiment. The physics is real. It has been tested, and the clocks have already disagreed. That is not a philosophical concern. It is a measured experimental result, confirmed in the 1970s by 4 cesium clocks and 2 airline tickets. The thought experiment that generated decades of uncomfortable classroom arguments goes like this. 2 twins begin their lives at the same moment. One stays on Earth, the other boards a spacecraft, accelerates to a high fraction of the speed of light, travels to a distant point, turns around, and comes back. The traveling twin ages less. When they reunite, they are no longer the same age. The traveler is younger. Students pushed back immediately, and their objection was reasonable. Motion is relative. If twin A moves away from twin B at 90% of the speed of light, you could equally describe it as twin B moving away from twin A at the same speed. If all motion is relative, and both twins are symmetrically moving, why does the calculation favor one over the other? Why does only the traveler end up younger? The answer is acceleration. The traveling twin changed velocity to stop at the destination, reverse course, and return. The spacecraft had to decelerate and then accelerate again in the opposite direction. That involved real, measurable force, the kind that presses you into your seat and that every accelerometer would register. The twin who stayed home felt none of it. The symmetry between the 2 world lines is broken by the act of changing direction. The twin who accelerated aged less. The difference is real. All of this remained a thought experiment until October of 1971. 2 physicists, Joseph Hafele, working at Washington University, and Richard Keating from the United States Naval Observatory, arranged to carry 4 cesium atomic clocks on commercial airline flights around the world. Cesium clocks keep time by tracking the microwave frequencies of cesium atoms and are accurate to billionths of a second over days of operation. They are sensitive enough to detect the tiny time discrepancies that relativity predicts at aircraft speeds. The plan? Fly 3 clocks around the world eastbound, then fly 3 clocks around the world westbound, and compare each against the 4th clock that remained on the ground. Eastbound flights travel in the direction of Earth's rotation and thus move faster relative to Earth's rotational center, increasing the special relativistic time dilation effect. Westbound flights move against the rotation and experience a different balance of effects. Einstein's equations predicted specific numbers. The eastbound clocks would show a net loss of around 40 nanoseconds. The westbound clocks would show a net gain of around 275 nanoseconds. Both effects arise from the combination of velocity-based time dilation and gravitational time dilation at altitude, which pulls in the opposite direction. The measured results. The eastbound clocks lost 59 nanoseconds. The westbound clocks gained 273 nanoseconds. Each matched the prediction within the experimental margin of error. 59 nanoseconds is a sliver of time so small no human nervous system can detect it. The clocks could. The clocks recorded a genuine, permanent, measurable age difference between themselves and the clock that stayed on the ground. The twin who traveled aged differently from the twin who did not. The result was published in a scientific journal and has been confirmed by every subsequent precision measurement. Time dilation is not a consequence of mathematics that might turn out not to apply to physical clocks. Physical clocks confirm it directly, and the scales involved are about to become significantly less abstract. Every navigation app, every turn-by-turn direction, every delivery driver following a route on a screen, every ship in open ocean using satellite positioning, every aircraft calculating ground track, every ambulance responding to an address. All of them are running a physics experiment, continuously, with results that would stop working within days if the physics turned out to be wrong. The constellation of satellites that provides global navigation orbits at an altitude of roughly 20,200 kilometers. Each satellite carries an atomic clock, and those clocks transmit precise time signals down to receivers on the ground. A receiver listens to several satellites simultaneously, measures the time delay of each signal's arrival, and uses those delays to calculate its own position. The accuracy of the final position depends entirely on the accuracy of the time measurements. Small clock errors mean large position errors. The satellites are moving. They orbit at roughly 3.9 kilometers per second relative to Earth's surface. Special relativity predicts that a clock in motion runs slower than a stationary clock. At orbital velocity, the satellite clocks lose about 7 microseconds per day compared to ground-level reference clocks. The satellites are also at altitude, where Earth's gravitational pull is weaker than at the surface. General relativity predicts that clocks in weaker gravitational fields run faster than clocks in stronger ones. At 20,200 kilometers, the gravitational effect runs opposite to the velocity effect and is larger, causing the satellite clocks to gain roughly 45 microseconds per day. Subtract the velocity-based slowdown from the gravity-based speedup, and the net result is that each satellite clock runs ahead of ground-level clocks by 38 microseconds per day. Light travels approximately 11 kilometers in 38 microseconds. If the satellite clocks and ground clocks diverge by that amount without correction, the calculated distances go wrong by roughly 11 kilometers every day. By the end of a week, an uncorrected system places you in the wrong neighborhood. By the end of a month, the wrong city. Engineers solved this before the first navigation satellite went live. They calculated the exact relativistic offset that each satellite clock would accumulate and then manufactured those clocks running at a slightly adjusted frequency before launch, deliberately slower to compensate for the relativistic gains they would accumulate in orbit. The correction was built into the hardware based on Einstein's equations, before any satellite had flown, before any measurement could confirm it. When the satellites launched and the clocks were compared, they ran exactly as the equations had predicted. Every time you use satellite navigation, you are depending on a system whose engineers trusted relativity enough to pre-correct for it before launch. The experiment runs continuously on every device that uses satellite positioning. The system works. That means the prediction was right. That means time dilation is real at the precision of 38 millionths of a second per day. Satellites in orbit are not the only place in nature where time dilation makes itself visible in ways that cannot be ignored. Something much smaller and much older does the same thing every single day, using nothing but speed and the depth of the atmosphere between it and the ground. Something is passing through you right now. You cannot feel it, see it, or detect it with any instrument you own, but the particles are there, and they have been arriving continuously since long before anything lived on this planet. They are called muons. They come from the upper atmosphere, and they should not exist long enough to reach you. Muons are subatomic particles about 200 times heavier than electrons. They carry an electric charge, and they decay, transforming spontaneously into lighter particles after a fixed average lifetime. That lifetime, measured carefully in laboratories around the world, is 2.2 microseconds, 2.2 millionths of a second. Even moving at the speed of light, a particle with that lifetime covers only about 660 meters before half of any sample has already decayed. Cosmic ray muons are born 10 kilometers above Earth's surface. High-energy protons streaming in from deep space slam into the nuclei of nitrogen and oxygen high in the atmosphere and produce showers of secondary particles. Muons are among those secondaries. They are created, they begin moving downward, and they begin their countdown toward decay. The arithmetic seems to make their arrival at sea level impossible. The drop from creation to the ground is 10 kilometers, and 660 meters is a fraction of that distance. Only an incredibly tiny fraction of muons should survive the full descent. Yet physicists, counting muons at sea level, find billions arriving every day. The measured survival rate is far higher than the rest frame calculation predicts. The resolution is time dilation, and it works exactly as predicted. Muons travel at roughly 99.4% of the speed of light. At that speed, the Lorentz factor is approximately 11. From the perspective of a physicist measuring them on the ground, the muon's internal decay clock runs 11 times slower than a clock at rest. The effective lifetime stretches from 2.2 microseconds to roughly 24 microseconds, long enough for a particle moving at near light speed to cover the 10 kilometers from creation altitude to sea level. Look at the same situation from the muon's own frame of reference, and the calculation changes form but stays consistent. The muon does not experience its clock as running slow. Its processes proceed at their normal rate. What has changed from its frame is the distance. Length contraction at 99.4% of light speed compresses the 10-kilometer atmosphere to under 1 kilometer in the muon's reference frame. The muon simply crosses a much shorter distance in its normal lifetime. Two completely different calculations, two completely different physical pictures, both arriving at the same answer. The muon reaches the ground. Both perspectives are valid. Neither is more correct than the other. The muons striking the ground are the traveling twin of the classic thought experiment. They are particles that departed from a point 10 kilometers up, moved at near light speed, and aged less than the universe around them aged. They arrive alive when they should have decayed. The sky overhead is continuously raining this experiment down. Every square meter of ground receives multiple muons per minute without interruption. The physics producing each individual arrival is the same physics that governs any ship traveling near the speed of light. The same equations, the same Lorentz factor, the same contracted distance or dilated time depending on which frame you occupy. The muon does not know it is proving Einstein right. It just survives. And it does so by the millions. Every hour, in every city, on every continent, under every square meter of sky. The Lorentz factor has a denominator, and the denominator is the problem. The formula takes the quantity 1 minus the square of your speed as a fraction of light speed, extracts its square root, and places the result below a numerator of 1 to produce gamma. When your speed is 0, the expression under the square root is 1. The denominator is 1, and gamma is 1. As speed increases, the quantity inside the square root decreases. The denominator shrinks. Gamma rises. At 99% of light speed, the quantity under the square root is about 0.02. Small, but still a real number. The denominator sits at roughly 0.14, and gamma reaches 7.09. At 100% of light speed, the quantity under the square root is 0 exactly. The denominator is 0. Dividing by 0 does not produce a very large number. It produces no defined result at all. The mathematics breaks down completely at that point. And the reason it breaks down is that the result it would need to produce is infinite. The energy required to reach exactly the speed of light is boundless, without ceiling, without any finite value that could ever be achieved. The infinity is built into the geometry of space-time itself, a structural feature of how the universe handles the relationship between mass, velocity, and energy. No future discovery will change it. An object with any mass cannot reach the speed of light for the same reason that a finite number cannot reach its own unlimited growth. The rules do not permit it. The practical consequence arrives well before the limit. Each additional fraction of speed past 90% costs more than the fraction before it, by a margin that grows as you approach the ceiling. Go from 0 to 90% and call that 1 unit of energy. Go from 90 to 99% and you spend roughly 6 more units. Go from 99 to 99.9% and you spend yet another comparable block, matching what you spent on everything before combined. Each decimal 9 in the speed fraction costs as much as all preceding 9s together. What makes this particularly unforgiving is how small the speed gain is compared to the cost. The difference between 99% and 99.9% of the speed of light is less than 1% of total velocity. A modest increase in raw numbers, the view through the forward window changes incrementally. The time dilation ratio deepens, the searchlight effect intensifies, but nothing dramatic announces that you have just spent the equivalent of your entire prior investment. The universe charges the full price for a change the speedometer barely registers. The energy wall rising toward the speed of light is a different species from conventional engineering problems. Those have solutions: better materials, more efficient designs, larger reactors, more time and capital. The energy requirement approaching light speed does not yield to any of those approaches. No material is strong enough, no reactor efficient enough, no funding large enough to overcome a mathematical requirement that approaches infinity. The wall is a property of reality, not a property of current human capability. Every proposal for near light speed travel confronts this wall eventually. The only theoretical ways around it involve moving the destination rather than the ship, or bypassing the velocity relationship through some geometry of space-time that has its own formidable problems. But first, before the workarounds, it is worth seeing the energy cost stated plainly in concrete terms that the imagination can hold. 1 kilogram. Hold it in your hand, a small bag of rice, a moderately sized book, a liter of water. That single kilogram of inert matter, starting from rest, is the mass under discussion. A spacecraft comes later. For now, just the kilogram. To accelerate that single kilogram to 99% of the speed of light requires energy roughly equivalent to 6 of the atomic bombs that destroyed Hiroshima in 1945. 6 separate nuclear detonations, each capable of leveling a city in an instant, directed entirely at the task of pushing 1 kilogram of matter to near light speed. The Hiroshima comparison is not chosen for drama alone. It is chosen because it communicates scale in a way that abstract energy units cannot. A kiloton of energy is difficult to picture. A weapon that destroyed a functioning city in a moment is not. Multiplying that by 6, then realizing that 6 such events represent the cost of moving 1 kilogram, begins to give the problem its proper weight. Now scale toward anything resembling a crewed spacecraft. Human beings require space, food, water, air, temperature regulation, radiation shielding, and instrumentation. The shielding alone, necessary to survive the interstellar medium at near light speed, weighs thousands of tons of dense material. Add life support systems, structural framework, navigation computers, and propulsion equipment, and a minimal crewed interstellar vessel, by any engineering estimate, weighs somewhere between 5,000 and 50,000 tons. Multiply the per kilogram energy cost by 10,000 tons, and the result climbs into territory that strains comparison. The total annual electrical energy output of every power plant currently operating on Earth, combined, falls short of what the calculation demands. Running the entire energy production of human civilization for years, pouring every joule into a single launch event, and achieving perfect efficiency at every step of the conversion would still fall short of the energy budget for one crewed ship at 99% of light speed. Perfect efficiency is not achievable. Every known propulsion mechanism wastes a significant fraction of its input energy as heat, radiation, and exhaust mass moving in unhelpful directions. Real-world efficiencies reduce the available energy budget further, requiring the power input to be larger still to achieve the same result. And all of this only addresses 99%. The calculation above does not reach 100. To reach 99.9% doubles the energy bill. 99.99 doubles it again. The bill keeps doubling as each decimal 9 is added to the speed, approaching a total that cannot be financed by any physical quantity. The universe has stated its price clearly, in a currency of energy, in quantities that have no precedent in human experience. The machines that have come closest to paying it, even fractionally, are among the most ambitious things our civilization has ever attempted. Some of them were almost built. One was killed by a treaty. Another existed only on paper but was drawn with extraordinary precision. The history of that ambition is worth knowing. In the late 1950s, a physicist named Freeman Dyson sat down with an engineer named Ted Taylor and a question that most of their colleagues considered too strange to take seriously. What if the most powerful tools humans had ever invented could be turned into engines? The tools in question were nuclear weapons. Each one released more energy in its detonation than any chemical process could produce in comparable mass. The weapons existed, they worked, and the energy they released was theoretically recoverable as thrust if the problem of directing it could be solved. Dyson and Taylor believed it could be. They called the project Project Orion. The concept required a large plate of thick metal at the rear of the spacecraft. A nuclear device, ejected behind the plate, would detonate. The fireball would push the plate. The plate, connected to the main body of the ship through a shock-absorbing system, would push the ship. Repeat at intervals of several seconds using a magazine of devices carried on board. Each detonation adds velocity. The cumulative effect, sustained across a large enough number of devices, produces a spacecraft moving at a meaningful fraction of the speed of light. Dyson calculated that a vehicle built on this principle could reach between 3 and 10% of the speed of light, depending on the number and yield of the devices carried. At even the lower end, 3%, a spacecraft launched toward the nearest star systems would cover distances that would take chemical rockets millions of years in a time frame measured in centuries. No other technology available in the 1960s approached these numbers. The project was not entirely theoretical. Engineers built small-scale prototypes using conventional explosive charges to test the pusher plate concept. The aerodynamics of ejected material and the engineering of shock absorption received serious analysis. Dyson believed genuinely that with political will and adequate funding, humanity could have launched the first interstellar probe by the early years of this century. What killed it was the Partial Nuclear Test Ban Treaty, signed in 1963. The agreement prohibited the detonation of nuclear devices in the atmosphere and in space, which was precisely where Project Orion's engine would have operated. The treaty was designed to prevent atmospheric fallout from contaminating the biosphere. It accomplished that goal and, as a consequence, cancelled the most concrete interstellar propulsion program the engineering community had ever produced. 20 years later, a different answer emerged under the name Project Daedalus. This study, produced by the British Interplanetary Society through the 1970s, asked what a serious unmanned probe to Barnard's star, about 6 light-years from Earth, would actually require in engineering terms. The answer was a 2-stage fusion rocket burning small pellets of deuterium and helium-3 at a rate of 250 per second. The projected cruise speed was 12% of the speed of light. The journey to Barnard's star would take 50 years. The total mass of the vehicle was 54,000 tons, the overwhelming majority of that being fuel. The scientific payload was a few hundred tons. There was no deceleration stage in the design. The probe would fly past Barnard's star and keep going, transmitting data during the hours of closest approach and then disappearing into the void beyond. A 50-year journey for a few hours of observation, and a signal requiring 6 years to return to Earth. Both projects taught the same lesson at different scales. The physics permits it, the engineering demands everything you have and then asks for more. Each design dreamed faster than any civilization has yet been able to build. In 1960, a physicist named Robert Busard published a proposal that seemed to answer the hardest question in interstellar propulsion. Where does the fuel come from? Not from tanks carried at launch, which would need to be impossibly massive, and not from depots planted in advance, which would require already being able to travel between stars. The fuel, in Busard's proposal, would come from space itself, continuously, for the entire duration of the journey. The interstellar medium contains hydrogen, about 1 atom per cubic centimeter on average in the regions between stars. hydrogen is the fuel for fusion reactions. If a spacecraft could collect that hydrogen as it flew, funnel it into a fusion reactor, and use the energy to accelerate, the ship would draw propulsion from the medium it was traveling through. The faster it moved, the more hydrogen it swept up per second, the more thrust it generated, the faster it moved. In principle, this cycle could sustain continuous acceleration indefinitely. The electromagnetic scoop needed to gather the hydrogen would be enormous, extending hundreds of kilometers ahead of the ship, shaping the diffuse gas into a stream leading toward the reactor inlet. Busard published the concept in the journal Acta Astronautica, and the physics community took it seriously. Science fiction absorbed the idea almost immediately. The Busard Ramjet appeared in novels and stories throughout the 1970s as the standard model for starship propulsion, plausible enough to be used without explanation, beautiful enough to stick. For a decade, it occupied that comfortable position between confirmed science and speculation, the kind of concept that appeared rigorous because it emerged from real physics and real equations. Then the detailed analysis arrived, and the details were unkind. The first problem is density. 1 atom per cubic centimeter sounds like it might be enough. The arithmetic says otherwise. To collect 1 gram of hydrogen per second at that density, the scoop would need to sweep a volume so large that its electromagnetic structure would need to span a region approaching the scale of a planetary system. The engineering required to maintain a coherent magnetic field of that size from a moving spacecraft at relativistic speeds, in the presence of the interstellar plasma it is trying to collect, goes well beyond any technology anyone can plausibly envision. The second problem is the fusion reaction. Proton-proton fusion, the reaction that powers stars, runs extraordinarily slowly even inside stellar cores. Stars achieve it only because they contain gravitational masses of hydrogen and operate over billions of years. A compact, human-built reactor would need to force the same reaction at rates that stars achieve only because of their tremendous scale. The third problem may be the most fundamental. The act of scooping hydrogen creates drag, intercepting particles from the interstellar medium and redirecting them exerts a backward force on the spacecraft. At the densities and speeds involved, physicists calculated that the drag from the scooping process likely matches or exceeds the thrust that the collected hydrogen could generate. The engine would fight the ship as much as it would push it. The Busard Ramjet remains one of the most elegant ideas in the history of interstellar propulsion. Elegant ideas deserve honest evaluation. The evaluation came and found that the universe does not cooperate with the elegance quite as Busard hoped. But sometimes, a beautiful theory points toward a real solution from an unexpected direction, sized not for a crew, but for a chip. The history of interstellar propulsion proposals is a history of thinking large and running into physics. Project Orion needed detonations forbidden by international treaty. Project Daedalus needed 54,000 tons of fuel. The Busard Ramjet needed a scoop the size of a planetary system and a fusion reaction no compact reactor could sustain. Every design that reached for the stars did so with enormous mass, enormous energy, and engineering demands that pushed toward the impossible. In 2016, a team working under the name Breakthrough Starshot inverted the strategy. Instead of making the spacecraft larger and more powerful, they made it smaller until the energy requirements became achievable. The spacecraft in the Breakthrough Starshot concept is not a spacecraft in the conventional sense. It is a chip, a single gram of microelectronics, carrying cameras, sensors, a power source, and a communication transmitter. Mounted to that chip is a sail, roughly 4 meters across, made of material thin enough to be measured in layers of atoms, reflective enough to bounce laser light efficiently. The entire probe, chip, and sail combined weighs about 1 gram. The accelerator is not on the ship, it is on the ground. A laser array, designed to output 100 gigawatts of power in a focused beam, illuminates the departing sail for a few minutes as it rises away from Earth. Light exerts pressure on any surface it strikes, and while that pressure is negligible from ordinary light sources, 100 gigawatts focused on a gram-scale sail produces acceleration measured in thousands of gravities. The sail and the chip riding it reach 20% of the speed of light within minutes. 20% of light speed is not the 99% that makes time dilation emotionally devastating. The Lorentz factor at that speed barely moves above 1. The journey to Proxima Centauri at 20% of light speed takes about 21 years from Earth's perspective. No human could ride the probe, both because no human fits on a 1-gram chip and because the acceleration phase would be lethal for any biological passenger. The probe arrives at Proxima Centauri as a machine, gathers data during the hours of closest approach, and transmits the results back. The signal takes 4 years to reach Earth. Total time from launch to data receipt, roughly 25 years. The project announced $100 million of initial funding and recruited engineers from several research universities to work on the technical challenges. Those challenges are considerable. The sail material must withstand 100 gigawatts of illumination without being destroyed, which requires reflectivity and thermal tolerance beyond anything currently in production. The laser array must maintain a coherent beam across the full acceleration distance, requiring atmospheric correction systems at scales that do not yet exist. Without a braking mechanism, the probe cannot orbit its destination. It can only fly past. These are engineering challenges, not violations of physics. Every one of them is the kind of problem that advances in manufacturing, optics, and materials science could plausibly address over the coming decades. The concept requires no new physics. It requires building difficult things better than humanity currently can. That puts breakthrough Starshot in a category by itself among interstellar proposals. Technically unrealized but physically sound. Ambitious, but not fantastical. A gram of silicon and metallic film, sailing at a fifth of light speed, launched by light, arriving at the nearest stars within a human generation. The probe would carry everything except the one propellant that could make it fast enough for human travel. And that propellant is the reason the largest ambitions in interstellar flight remain theoretical. Every propulsion concept ever built or seriously imagined involves an energy conversion with waste. Chemical rockets burn fuel and produce exhaust that carries away most of the released energy in directions that do not help. Nuclear fission converts less than 1% of the rest mass energy of its fuel into useful output. Nuclear fusion reaches about 0.7%. The remaining 99.3% stays locked in the products, unrecovered. Antimatter annihilation is the one exception in known physics. When a particle of ordinary matter meets its corresponding antiparticle, the pair annihilates completely. Every bit of rest mass energy converts into other forms with no remainder. The conversion efficiency is 100%. No engine in physics can do better, because no engine can extract more energy from a given mass than complete annihilation provides. The specific energy release is breathtaking in scale. 1 gram of matter reacting with 1 gram of antimatter produces energy equivalent to roughly 43 kilotons of chemical explosive. The weapon dropped over the city of Nagasaki released approximately 21 kilotons. 2 grams of fuel, each weighing less than a paperclip, releases more than twice that. A spacecraft powered by matter-antimatter annihilation would carry propellant measured in kilograms, where nuclear rockets require hundreds of thousands of tons. The catch is not that the physics is uncertain. The physics is precise. The catch is that antimatter does not exist in useful quantities anywhere humans can reach. The observable universe consists almost entirely of ordinary matter. Natural deposits of antimatter large enough to fuel a spacecraft have not been found anywhere humans can reach. Antimatter can be manufactured. Particle accelerators produce antiprotons by firing proton beams at targets at very high energy. The production rate at all of Earth's accelerator facilities combined is on the order of a few nanograms per year. A nanogram is 1 billionth of a gram. Manufacturing a single gram at that rate would require billions of years, at a cost running to trillions of dollars. Storage is a separate and equally fundamental obstacle. Antimatter cannot contact any physical container. Metal tanks, glass bottles, any material enclosure triggers annihilation on contact. The stored antimatter must be suspended inside a perfect vacuum by precisely maintained magnetic fields, isolated from every surface at all times. Any failure of the magnetic containment, any brief interruption of the field, means the suspended antimatter contacts the nearest material. The energy release depends on how much was stored. For a meaningful fuel supply, that energy release is catastrophic by definition. The perfect fuel exists as a category in physics. Its performance is unmatched by anything else. Interstellar travel on antimatter propulsion is consistent with the laws of thermodynamics and special relativity. The universe does not provide it in a form that can be collected, stored, or safely used. The best energy source in known physics sits behind barriers of production, cost, and containment that show no clear path to resolution. At 99.9% of the speed of light, a ship carrying any fuel source has paid the energy bill that this journey has described. What that speed does to the universe outside the window is something the numbers alone cannot fully prepare you for. At 99.9% of the speed of light, the Lorentz factor reaches 22.37. More than 22 years now pass outside for every year that passes on the ship. A 2-year mission from the crew's perspective corresponds to nearly 45 years of elapsed time beyond the hull. The temporal gap has grown large enough to span a generation. People born while you were in transit have reached adulthood before you return. But the sky has done something that the time dilation numbers cannot prepare you for. At every previous speed, the visual changes followed a progression: slight blue shifting, then star crowding from aberration, then dramatic color sweeps, then forward compression as the rear sky drained to nothing. At 99.9%, that progression has reached its extreme. Almost all detectable light now arrives from directly ahead. The searchlight effect has concentrated photons from an entire sphere of space into a narrow forward beam. Aberration at this speed is so severe that photons arriving from directions nearly perpendicular to your path still appear to come from almost directly ahead. The forward sky blazes with an intensity that comes from the same stars concentrated together, their photons arriving through angles that have collapsed to near zero. Behind the ship, the sky has gone dark, genuinely dark, the way a sealed room with no light source is dark. Every star behind you has had its emission shifted so far into the radio spectrum that no optical instrument can detect it. The stars themselves are still there, still radiating, still sending photons in your direction. Your velocity has robbed those photons of all frequency that any optical sensor can measure. The rear of the ship faces a universe that is real and present but entirely undetectable by human eyes or conventional instruments. And then there is the afterglow. The cosmic microwave background pervades every cubic centimeter of the universe, remnant thermal radiation from the era when matter and light decoupled and photons first traveled freely through space. Billions of years of expansion have stretched those photons into microwaves at 2.7 Kelvin, invisible and harmless to any stationary observer. At 99.9% of light speed, the forward cosmic microwave background has blue shifted into the visible spectrum. You can see the oldest light in the universe with your bare eyes. What you see is a faint ring of light encircling the central blaze of the searchlight effect, a halo wrapping around the concentrated starlight. That ring is the afterglow of the universe's first moment of optical transparency, photons traveling, since 380,000 years after the beginning, compressed by your velocity from microwaves into frequencies your retinas can register. Two separate epochs of cosmic history have arrived at your eyes simultaneously. The forward starlight represents billions of years of stellar evolution. The surrounding glow represents the oldest event in the observable universe, both merged by your speed into a single overwhelming visual event. Behind you, absolute darkness. Ahead, everything at once, including the first light the universe ever set free. The universe has been working up to this for the entire length of this journey, and what it does to a body aboard the ship at these speeds, beyond the visual, is a different and considerably more serious matter. At 99.9% of the speed of light, the universe stops being inhospitable and becomes something worse. The cosmic microwave background, that ancient glow of the Big Bang that pervades every cubic centimeter of existence, has been quietly changing as your speed climbed. At 90%, it entered the infrared, brushing the lower edge of what cameras could detect. At 99%, it crossed into the visible range, that ghostly ring of light encircling the forward view. At 99.9%, it has climbed further still. The photons pressing against your hull from ahead are no longer at microwave frequencies or infrared or even visible light. They are ultraviolet. Some have crossed into the soft X-ray range. This is what a Lorentz factor of 22.4 does to background radiation that started at 2.7 Kelvin. The blue shift multiplies the frequency of every incoming photon by a factor of 22. Microwaves become ultraviolet. Ultraviolet climbs toward X-rays, and X-rays penetrate. The interstellar hydrogen, which at 70% of light speed already delivered a fatal radiation dose every second, has now made that figure irrelevant by orders of magnitude. Researchers who modeled the radiation hazards of relativistic travel calculated that the combined particle and photon bombardment at speeds approaching 99.9% of light speed produces radiation exposure in the report millions of rem per second. 1,000 rem is lethal to a human being without treatment. Millions of rem per second means the relevant measurement is no longer a medical unit, but a statement about physics. The only comparison that comes close is the radiation field at the core of an operating fission reactor, which would kill an unshielded person in seconds. At this speed, the effective radiation intensity exceeds that figure by millions of times. The void your ship is flying through has become, from a biological standpoint, the most hostile environment in the known universe. Every hydrogen atom in the interstellar medium slams into the forward hull at relativistic energies and produces a cascade of secondary particles: neutrons, pions, muons, gamma rays. A thin metal hull makes this worse, not better, by turning each primary impact into a spray of secondary radiation that irradiates the interior more thoroughly than the initial beam ever could. The shielding at the bow of the ship is not an engineering precaution at this speed. It is the only reason anything inside remains intact. Meters of dense material stand between your survival and instantaneous biological destruction. The shield itself erodes under the energy it absorbs, slowly sacrificing itself to keep the interior livable, and the universe beyond your windows gives no sign of any of this. The forward sky blazes with the concentrated light of every star in the visible universe, crowded into a brilliant forward oval by aberration, colors shifted far into the blue and beyond. The rear sky is absolute black. The visual spectacle is extraordinary, the kind of thing a person would cross the galaxy to witness if the crossing itself were not what was doing the killing. The radiation fields are invisible. The destruction is invisible. The danger arrives as particles you cannot see and photons your eyes were never built to register. Inside the ship, though, none of that registers directly. And that is the part nobody talks about when they describe what relativistic travel would feel like. Because the most unsettling thing about traveling at 99.9% of light speed is not the danger outside. It is the silence within. Your heartbeat is completely normal. That fact deserves more weight than it usually gets. At 99.9% of light speed, with the cosmic microwave background delivering X-ray photons against your hull, with every hydrogen atom in the interstellar medium slamming into the ship's forward face at relativistic energies, with time itself running 22 times slower for you than for any observer watching from outside. Your heartbeat is completely, indistinguishably normal. Your food tastes the way it always has. The air holds its usual temperature. Your clocks tick once per second, as they always have. This is the cruelest thing that special relativity does, and it does it deliberately, in the sense that it is a fundamental feature rather than an accident. The principle of relativity states that the laws of physics are identical in every non-accelerating reference frame. This means that if you are inside a ship moving at any constant velocity, no experiment you conduct inside that ship can tell you that you are moving. Physics does not permit it. Velocity is relative. Motion requires something to measure it against, and in the absence of an external reference point, you are simply at rest. From your frame of reference, the universe outside is traveling past you at 99.9% of light speed. Time dilation is happening to the universe, which is the moving party from your perspective. Your frame is as valid as any other. Your instruments record nothing unusual. Your body feels one gravity, if still accelerating. Heartbeat, breathing, digestion, neurochemistry, all baseline, all ordinary. The storm is real. The radiation is real. Somewhere behind you, people who watched you launch are aging at 22 times your rate. The gap between your life and theirs widens every second by a ratio that ensures you will never share a synchronized moment with them again. You cannot feel any of it. Consider what that actually means. The clocks on this ship are running correctly. They are keeping perfect time, ticking at exactly their designed rate, calibrated to the laws of physics that govern your frame. From within this frame, they are right. The clocks back on Earth are also running correctly, ticking at exactly their designed rate, and from within that frame, they are right too. Both sets of clocks are accurate. Both frames are valid. The discrepancy between them is not a measurement error. It is a fact of space-time geometry that no instrument inside this ship will ever be able to feel or register as anything other than perfectly ordinary ticking. There is no physical sensation of time slowing, no internal compass pointing toward the growing temporal distance behind you. Your nervous system, built over millions of years for a very different set of conditions, cannot detect a single second of the universe's strangest physics happening around you. You are the eye of the most extreme storm in physics. The violence is on every side. The calm is absolute where you sit. Something outside the ship, though, has discovered an extraordinary side effect of the physics. A phenomenon where one of the universe's most counterintuitive rules lights up with visible, eerie blue fire. The speed limit, embedded in the laws of physics, is not simply one number, it is two. The absolute limit, the one that governs all of space and time, is the speed of light in a vacuum, approximately 186,000 miles per second. Immovable, universal, enforced, without exception. But light does not always travel through a vacuum. Inside materials, inside glass and water and crystal, the electromagnetic field of a photon interacts with the atoms it passes through, and it slows down. Inside water, light travels at about 75% of the vacuum speed. Inside glass, roughly 2/3. Inside diamond, a fraction below half. The vacuum speed limit still applies to everything, but within a medium, the effective local speed of light is lower, and this creates a possibility that has no equivalent in everyday physics. Charged particles from nuclear reactions, electrons and protons, and heavier nuclei moving at very high energies can travel faster than the local speed of light in a medium. They cannot beat the vacuum limit, but they can outrun the reduced speed of light in water. When they do, something remarkable happens. The particle passes through the medium faster than the electromagnetic disturbance of its passage can propagate. The light generated by its interaction with the medium piles up behind it the way a sonic boom piles up behind a supersonic aircraft. The overlapping wavefronts interfere constructively, producing a coherent cone of radiation emitted at a specific angle behind the particle's path. The radiation peaks at short wavelengths, in the blue and violet part of the visible spectrum. A Russian physicist named Pavel Cherenkov described and characterized this phenomenon in 1934, working in Moscow. Two colleagues named Ilya Frank and Igor Tamm provided the theoretical explanation 3 years later. All three received the Nobel Prize in Physics in 1958. The color is real, it is eerie, and it has become one of the most recognizable sights in nuclear science. Spent fuel pools at nuclear power plants glow with Cherenkov light, an electric blue-violet illuminating the water around the fuel assemblies. Research reactors filled with water produce the same glow around the core during operation. Hollywood gets this wrong with remarkable consistency, depicting nuclear environments as green. The actual color is blue-violet, sharp and clean, the color of a phenomenon happening in real time as particles break the local speed limit built into the medium. The effect extends to something far more personal. Astronauts aboard the International Space Station have reported seeing brief blue flashes of light with their eyes closed, especially during sleep periods. In the darkness behind their eyelids, something produces light. The cause is cosmic rays, high-energy particles from space, passing through the vitreous humor of the eye. The vitreous humor is mostly water. The cosmic ray is moving faster than light moves through water. The result is Cherenkov radiation generated directly inside the astronaut's own eyeball, triggering the photoreceptors at the retina without any photon ever arriving from outside. Even inside a human body, traveling through space, relativity can make itself visible. This same principle operates inside the largest particle physics experiments humanity has ever built. And those experiments have done something remarkable. They have measured, precisely and repeatedly, exactly what the speed limit feels like when you press against it from the inside. Beneath the Swiss and French countryside, buried in a circular tunnel roughly 17 miles in circumference, the most relativistic environment on Earth runs continuously. The Large Hadron Collider at the European Organization for Nuclear Research near Geneva accelerates protons in two beams, traveling in opposite directions around the ring, building up speed over the course of minutes, driven by superconducting radio frequency cavities that give each proton a small energy kick on every circuit. After thousands of laps, the protons reach their operating speed. In the most recent operational run, that speed is 99.9999991% of the speed of light. 9 nines and a 1. That last vanishing fraction away from the absolute limit represents the gap between the achievable and the unreachable. At that speed, the Lorentz factor for each proton is approximately 7,454. 1 second of time in the proton's reference frame corresponds to over 2 hours of time in the laboratory. The 27-kilometer ring of the collider, from the proton's perspective, is length contracted to roughly 12 feet. A structure that spans most of the area between Geneva and the Jura Mountains, containing thousands of superconducting magnets and detection systems, appears to the proton as a room you could cross in a few steps. Each proton makes approximately 11,000 circuits of the ring per second, as measured by laboratory clocks. From its own perspective, it is doing something closer to a leisurely walk through a very short corridor. The machine works precisely because the engineers who designed it calculated these relativistic effects and built them into every magnet current, every cavity timing, every detector geometry. Particle lifetimes in the detector volumes extend exactly as the Lorentz factor predicts. The entire operation is a continuous confirmation of special relativity, run trillions of times per second. The direct measurement of what happens when you push mass toward the speed limit was conducted with remarkable simplicity decades earlier. In 1964, a physicist named William Bertozzi at the Massachusetts Institute of Technology accelerated electrons using a linear accelerator and measured both their kinetic energy and their actual velocity at each stage. As energy increased, velocity increased too, but the relationship was not proportional. Each additional unit of energy produced less additional velocity than the one before. The electrons climbed toward the speed of light on a curve that flattened progressively, asymptotically approaching it without ever reaching it. At the highest energies in Bertozzi's experiment, the electrons were traveling at over 99% of the speed of light. Doubling the energy again moved their velocity by only a fraction of a percent. The speed of light was a horizon they approached, but could never cross, receding at exactly the rate physics required. The speed limit is not a theory awaiting challenge. It is a measured fact, confirmed in that linear accelerator in Cambridge, confirmed in every particle collider built since, confirmed at energies far beyond anything achievable in 1964. Every proton in the Large Hadron Collider is proof, circling its contracted ring, aging at 1/7,000th the rate of the physicists watching the screens. And yet, a paper published 30 years after that experiment proposed something that made physicists stop and read it twice. Miguel Alcubierre was a graduate student in theoretical physics at Cardiff University when he submitted a paper in January 1994 that changed the way scientists thought about the speed limit. The paper was titled "The Warp Drive: Hyperfast Travel Within General Relativity." The title alone was enough to make physicists pay attention. Alcubierre had not found a loophole in special relativity. He had done something more subtle. He had looked at what general relativity, Einstein's theory of gravity, actually permits space-time itself to do. What he found was that Einstein's equations allow space-time to move. The universe is already doing this. The expansion of the cosmos carries distant galaxies away from each other at speeds exceeding the speed of light, not because the galaxies are moving through space faster than light, but because the space between them is stretching, creating distance without any object locally traveling faster than light. Special relativity governs motion through space. It does not govern the motion of space itself. Alcubierre's metric described a configuration of space-time curvature that would contract space in front of a ship while expanding space behind it. The ship would sit inside a flat, undistorted bubble, experiencing no acceleration and no time dilation, while the bubble itself moved through the universe at whatever speed the space-time distortion required. The occupant would feel nothing unusual, age by only the travel time inside the bubble, arrive at a destination light years away having lived through the crossing, younger than anyone who watched them leave and waited. The problem that stopped every physicist who read the paper was the energy requirement. Maintaining the warp bubble required matter with negative energy density, exotic matter that has no confirmed macroscopic existence. The initial estimates were staggering, the equivalent energy of the entire mass of Jupiter in negative form, a quantity that dwarfs every energy source in the solar system. Over the following decades, researchers worked to reduce this figure through geometric refinements. A researcher at a laboratory inside the National Aeronautics and Space Administration proposed modifications to the bubble's shape that lowered the requirement by many orders of magnitude, though still to levels requiring exotic matter that has never been observed. Then the picture changed. In 2024, a team at a research group called Applied Physics published a paper describing a subluminal warp drive requiring only positive energy. The bubble would travel below the speed of light, but still at extraordinary velocities with no exotic matter at all. 1 year later, the same group published a model they called a physical warp drive, relying entirely on positive energy gravitational effects. Alcubierre himself reviewed the work and stated publicly that he endorsed it. 2 publications, in 2 consecutive years, pushing the concept from mathematical curiosity towards something that at least speaks the language of real physics rather than requiring matter. The universe has never been observed to produce. The energy requirements remain far beyond anything human civilization can produce. The gap between the physics being theoretically valid and the engineering being remotely achievable is measured in centuries, possibly more. But the physics is valid. The warp drive is not ruled out by known laws the way perpetual motion is ruled out by thermodynamics. It is a genuine solution to Einstein's field equations. There is, however, a deeper problem with faster-than-light travel that has nothing to do with energy. It is woven into the logical structure of the universe itself. Here is the argument that has ended every serious discussion of faster-than-light travel for over a century. Stated as plainly as possible, pick any reference frame, any observer moving at constant velocity through space. In special relativity, all such frames are equally valid. There is no preferred frame, no absolute rest. The laws of physics look the same from all of them. This is the principle of relativity, the cornerstone of Einstein's entire framework. Now, suppose some technology allows a signal or an object to travel from point A to point B faster than light in one particular reference frame. Call it whatever you like. The label does not matter. What matters is the speed, faster than light. Apply a Lorentz transformation, the mathematical tool that converts coordinates between reference frames. In a frame moving at the right velocity relative to the first one, that same faster-than-light journey from A to B arrives before it began. The arrival at B, in this second frame, occurs before the departure from A. This does not arise from exotic conditions. It follows directly from the mathematics of special relativity for any speed exceeding the speed of light. In any reference frame combination, the principle of relativity permits. Faster-than-light travel, in any form, is mathematically equivalent to backward time travel in some valid reference frame. Follow the consequences. A faster-than-light communicator allows messages to be sent into the past. A reply to a message you have not yet written can arrive before you write it. You can read the reply, decide not to send the original message, and the reply now exists without a cause. The chain of causation, the principle that effects follow their causes in time, collapses. This is the grandfather paradox at its cleanest. If you can travel back before you were born and affect events, your own existence becomes contingent on a chain of events your existence disrupted. The scenario does not require anything exotic. The same mathematical machinery that gives you the faster-than-light capability also hands you the time machine automatically. In every reference frame that the principle of relativity requires you to treat as valid, there is no version of faster-than-light signaling that escapes this. The causality violation is built into the geometry. The logical structure of cause and effect is not a rule layered on top of physics. It is the structure within which physics exists at all. Every experiment ever performed, every piece of knowledge ever accumulated by science, was gathered by tracing chains of cause and effect in controlled situations. If causality fails, experiment fails. If experiment fails, knowledge itself loses its foundation. The speed of light is the speed of cause and effect. It is enforced not because some law was arbitrarily written that way, but because a universe without it would be self-contradicting at every observation simultaneously. What faster-than-light travel would reveal, if it were possible, is not the next star system. In some equally valid reference frame, it is yesterday. But there is something about the present moment that turns out to be almost equally strange, and it does not require breaking any speed limit to encounter. It only requires asking what now actually means for two observers who are simply moving at different speeds. Two people pass each other on a sidewalk. One is walking in one direction, the other in the opposite direction. Their velocities differ by perhaps 4 miles per hour. This is so ordinary an event that the laws of physics seem to have nothing interesting to say about it. Special relativity disagrees. Every observer has what physicists call a plane of simultaneity, the set of all events in the universe that, from their perspective, are happening right now. Two people at rest, relative to each other, share the same plane. They agree on what is happening simultaneously across any distance. Observers moving relative to each other do not share the same plane. Their slices of now are tilted relative to each other in the geometry of space-time. At everyday speeds, the tilt is negligible for everyday distances. Over distances of a few miles, the difference is unmeasurably small. Stretch the geometry out across the universe, though, and the tilt becomes dramatic. The Andromeda Galaxy is approximately 2.5 million light-years away. The two people walking past each other on that sidewalk, differing in velocity by 4 miles per hour, have planes of simultaneity that differ by roughly 2 days across that distance. From the perspective of the person walking in one direction, an event on Andromeda that counts as right now is 2 days later in calendar time than the event that counts as right now for the person walking the other way. They are separated by 4 miles per hour and a few feet of sidewalk. Their nows are 2 days apart at the distance of another galaxy. Neither of them is wrong. The universe does not have a preferred slice of now that all observers share. The present is not a universal constant. It is a relationship between an event and an observer, defined by the observer's state of motion. At relativistic speeds, this becomes extreme. A traveler moving at 99% of light speed has a plane of simultaneity tilted so steeply that events separated by light years in space are separated by decades or centuries in their now compared to a stationary observer's now. The traveler's present moment includes events that, from Earth's perspective, are centuries in the past or centuries in the future. Both perspectives are equally valid. There is no clock somewhere in space ticking out the true time. There is no master ledger recording what is actually happening at this moment. The universe contains no such thing. This realization that simultaneity is not absolute but relational, that now is personal, was one of the most philosophically disorienting results of Einstein's 1905 paper. Philosophers and physicists have debated its implications for over a century. If two observers can disagree about what is happening now at great distances, and neither is wrong, what does that say about the nature of time itself? It says something that pushes toward a question most people have never thought to ask. If the present is a matter of perspective, what about the past and the future? If now is not universal, are past and future any more absolute? The answer is strange, and it becomes hardest to avoid at the next extreme of speed. 6 nines. 99.9999% of the speed of light. The Lorentz factor at this speed is approximately 707. 1 year of traveler time corresponds to 707 years outside the ship. The universe beyond the hull ages at a rate that makes the time dilation at 99%, which seemed dramatic at a factor of 7, look almost gentle by comparison. The distance to Proxima Centauri, the closest star system to our own at 4.24 light-years, is length contracted in the traveler's frame by that factor of 707. The actual crossing, from the traveler's perspective, takes roughly 3.5 days of flight at close to light speed. Earth time elapsed, 4.25 years. Traveler time, 3.5 days. Now scale up. The Milky Way is approximately 100,000 light-years across. At 99.9999% of light speed, crossing the full diameter of the galaxy takes roughly 140 years of traveler time. The traveler ages 140 years. Outside the ship, 100,000 years of cosmic time pass. Every star in the Milky Way ages. Some burn out entirely. Species evolve and go extinct. 100,000 years of galactic history unfolds, while one human lifetime is spent making the crossing. Add more nines. At even higher fractions of light speed, the Lorentz factor climbs into the tens of thousands. The observable universe becomes theoretically traversable in a human lifespan, a journey requiring billions of light-years of travel in the universe's frame compresses, in the traveler's frame, to decades. A person could, in principle, travel from one end of the observable universe to the other and arrive having aged by perhaps a century. Outside, billions of years would have passed. Galaxies that existed when they left would be ancient relics or gone. Stars that shone on their departure date would have exhausted their fuel, collapsed, or dispersed. The universe would be measurably older, measurably colder, measurably darker. The traveler arrives in a cosmos that has aged by a span exceeding the current age of the universe. Nothing they knew remains. The civilizations that equipped and launched them have had billions of years to rise, transform, collapse, and either evolve into something unrecognizable or vanish entirely. The physics that govern their home planet still holds. The atoms are the same. The stars in this distant, ancient sky obey the same laws. But the context, the people, the cultures, the language they thought in, all of it is as thoroughly gone as the dinosaurs are gone from a modern city. Nothing they left behind is accessible, even in principle, because the light from their departure point, traveling at the same speed they were almost matching, has not yet reached where they are. The ship that could make this journey, if it existed, would carry a person who woke up every morning, ate breakfast, aged a day, and watched the universe outside grow old by centuries. Each morning the same, each evening the same. Outside, empires of stars rising and falling in the time it takes to drink a cup of coffee. There is a framework in physics that finds this situation less tragic than it sounds. A way of thinking about space-time that reframes the entire journey as something that, in a certain sense, is already complete. Here is the question. The relativity of simultaneity forces onto the table. If the present moment is different for different observers, and if neither observer's present is more real than the others, does that mean the past and the future are equally real? Philosophers call this eternalism. Physicists sometimes call it the block universe. The argument runs like this. You experience the present as uniquely actual. The past existed but no longer does. The future has not happened yet. Only now is real. This intuition has a name in philosophy: presentism, the view that only the present exists. Special relativity creates a direct problem for presentism. If two observers disagree about which events are happening right now, and both are correct, then the events each considers present are different. Events that observer A considers past are present for observer B. If only the present is real, then whether any given event actually exists depends entirely on who is asking and how fast they are moving. Reality becomes a property of the observer rather than of the event itself. Physicist and philosopher Hilary Putnam argued in 1967 that this result makes presentism untenable. If what is real depends on velocity, then real is not a coherent concept applied to events. The more consistent position, Putnam argued, is that all events, past, present, and future, exist equally. They are all equally part of the four-dimensional structure of space-time. The experience of time passing, of moving from one moment to the next, is real for the observer experiencing it, but the underlying structure contains all moments simultaneously. In this view, space-time is a four-dimensional object, a structure that extends through both space and time, containing every event that has ever happened and every event that will happen. Your birth is in there. Your death is in there. Every particle interaction since the Big Bang is embedded in the structure, not as something that will happen or that used to happen, but as a geometric feature of the block. What you experience as the flow of time is your world line traced through this object. You move along the time dimension, and the events you encounter are real as you reach them, but the structure contains them all, regardless of whether you have reached them. The implications are difficult to sit with. Physicists who endorse eternalism are careful to note that it does not trivially resolve questions about agency and choice. Those debates continue, but the framework does something useful for understanding what extreme relativistic travel actually means. The traveler who crosses the galaxy in 140 personal years, while 100,000 years pass outside, is not traveling to the future in any magical sense. They are tracing a path through the block that, in the time dimension, extends much less far than the paths of the people they left behind. Both paths exist. Both are real. The traveler and the civilization they departed from are equally present in the geometry of space-time, connected by structure, separated only by the shape of their world lines through it. One film captured this feeling better than any other, and it did so with a physicist's equations standing behind every frame. In 2014, a film called Interstellar arrived in theaters, carrying the unusual distinction of having its key scientific sequences. Designed by an actual theoretical physicist who had spent decades working at the edges of what general relativity permits. Kip Thorne, a professor emeritus at the California Institute of Technology, who would receive the Nobel Prize in Physics 3 years later for his central role in the detection of gravitational waves, worked as scientific consultant and executive producer on the film. His involvement was deep enough that the visual rendering of the film's central black hole, a massive spinning object called Gargantua, was computed directly from his equations. The result was accurate enough to generate a peer-reviewed paper published in a major physics journal. The film produced new science as a byproduct of trying to look correct. The sequence that has stayed with audiences longest involves a planet orbiting close to Gargantua. Because the black hole's immense gravity warps space-time severely in its vicinity, time near Gargantua runs measurably, dramatically slower than time at a safer distance. 1 hour spent on the surface of that planet corresponds to 7 years of time at a higher orbit. The protagonists spend roughly 3 hours on the planet's surface. When they return to the ship orbiting farther out, the crew member who waited for them has aged 23 years. He hands over a collection of video messages received from Earth over those years, decades of his life accumulated in an afternoon of theirs. The scene where the lead character watches those messages, seeing years of his daughter's life compressed into minutes of screen time, captures something no physics textbook diagram has ever managed to convey: what the emotional reality of time dilation actually feels like. The physics is correct, or very nearly so. The mechanism is different from velocity-based time dilation, driven by gravity rather than speed. But the underlying principle is identical. Time runs at different rates in different regions of space-time, and anyone who has spent time in the slower region returns to find that the faster world did not wait. The time dilation on Miller's planet requires a gravitational field that pushes the edges of plausibility, even for a black hole as massive as Gargantua, and physicists have noted the engineering details that strain credulity. But the core phenomenon, the mechanism, the mathematics of why time runs differently in curved spacetime near a massive object, is grounded in the same general relativity that engineers at navigation agencies correct for every day. What the film made visible to millions of people is the same truth encoded in special relativity's equations for velocity-based dilation. The universe does not guarantee that time flows at the same rate for everyone. Your time is yours. Synchronization requires proximity and shared motion. Go somewhere extreme, and you return to a world that has lived without you in ways you cannot recover. The story ends where the film ends, at a reunion across a gap measurable in decades of unclaimed life. And it ends, scientifically speaking, with the question the film deliberately leaves unanswered. What does the universe look like when you accept that even the speed of light is too slow to reach most of it? Here is the number that closes the door. Light travels at approximately 186,000 miles per second. In 1 year, that beam covers roughly 5.9 trillion miles. A beam leaving our star right now reaches Mars in about 12 minutes and Jupiter in 35. These numbers feel generous, almost friendly, as if the universe is a place a determined traveler could navigate. Then the scales shift. The nearest star system, Proxima Centauri, is 4.24 light-years away. A radio message sent to any civilization that might exist there arrives 4 years later. Their reply takes 4 years to return. 8 years of silence for a single exchange. Assuming anyone is listening, the Milky Way spans 100,000 light-years. A civilization broadcasting from the far side of our galaxy would have its signal arrive at Earth 100,000 years after transmission. Whatever sent that signal has had 100,000 years to change, collapse, or go silent before the first photon reaches anyone who might respond. And the Milky Way is one galaxy among an estimated 2 trillion in the observable cosmos. The Andromeda Galaxy sits 2.5 million light-years away. Light from their left, when the most sophisticated tool our ancestors possessed was a sharpened stone. The observable universe itself spans roughly 93 billion light-years, and galaxies at its edges are receding faster than light, carried by cosmic expansion. No signal sent today will ever reach them. Consider what this means for a traveler who has followed this entire journey, who watched the sky compress and fold into a blinding forward glow while the universe aged faster outside. Even that traveler, at 99.999 of light speed, cannot outrun the expansion at the universe's edge, cannot send a signal back before their origin civilization has risen and fallen 100 times over. The speed of light is the maximum. It is also, measured against what exists, almost nothing. The speed limit is not the tragedy. The size is the tragedy. The limit is set just high enough to make the universe tantalizingly visible across distances so vast that even the fastest possible travel leaves almost all of it permanently, cosmically out of reach. You can see light that left its source before the Earth formed. You cannot reach the place it came from. That is the shape of the universe we live in. We just needed the math to finally say it clearly.